So I have here two questions. Some values are already given in the tables. Now, what is question number 4? If the microprocessor sends linear address, this is given. Okay, to the paging, which paging directory is accessed and which page table entry is accessed. Okay, so linear address is split into binary into these fields. 12 bits, 10 bits, 10 bits. This is what we have. So if I want to do this 44, then this 20 is 00, 2, and then lots of zeros, right? 1, 2, 3, and then 4, 1, 2, 3, 4, 5, 6, 7, and then 8. This is offset, 12 bits. This is the page table, and this one is the directory, 10 bits. This is the rule. Question is, which paging directory is accessed?
0.
0 directory. Which page table is being accessed? Convert this one into hexadecimal. And what is the offset? 0. This is what we understand from 44. Let's go to 45. What is this one, 45? If what value is placed in the page table? This is page table. So what will be entry here? To direct linear address, which is this one, to physical address, which is this one. Now, but there are something more here. Let's solve this thing. Address is 2 and 7 zeros, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, and this one is 8. So this one is offset. This is page table, and this is the directory. Now question is, what is placed in the page table? So this means what is in here. Okay. Now how do we find here? So whatever is inside, actually that is the one which is coming outside, right? So what do I know this one? No. So what will be this one then? How can I find this one? Is this one, because this one plus this one is this one, right?
Yes.
So how can I find this one? This one minus this one. What is offset? 0. So I have to subtract 0 from the physical address. And what is the physical address? 30 million, right? Yeah. So 30 million minus 0 is 30 million. Whatever is here, that is coming inside. Okay? So the answer is, this is what you have.
Sir, we cannot say that.
Because this one plus this 0 will give me the physical address. Yes?
We cannot say that this is just 0A9.
Which one?
0A9, the last one, plus the big.
This one plus this one will give you this address. This inside is the address. This is the address. This is inside the table because this says placed in the page table. We are not talking about address to the page table. Okay, that's why. All right, let's do 22 from chapter 5. Write a sequence of instructions. I think this was in the homework. Sequence that cube the 8-bit number found in DL. So target is, this is question number 32. This is the target. That cube the 8-bit number found in DL. Load DL with 5. This one is equal to 5. Now write a code how it will be doing this one. Okay, so first we will say 5 to DL. Okay. First we will be doing first multiplication, which is the square, right? Say how do we do the square? AL multiplied by DL. And both have to be the same size, right? So we will say here move DL to AL. If I say mul DL, this will be DL times AL and the answer will be in AX. Multiplication, right? Now how do we do the, and AX means it? AH, right? Now it says make sure your result is a 16-bit number, right? Now, what do I do the next one? My answer is in both, supposedly, right? But now there is one thing you should note. This number is small. So this means that this value here is not needed. Our actual value is here because 5 times 5 will be 25. If this number you know is very big, not very big but at least a good like 100, 120, then multiply 120 with 120 will be a big number, more than a byte. Since this is 5, so obviously answer will be still a byte. So that's why my original value is, my answer of the first square is in AL, which is also a byte. Now again I can multiply with it DL. Mul DL, which will be again DL multiplied by AL. Now answer will be a 16-bit. Why? Because the before I have 25, right? Now multiply again, it will be X. Okay? How about the 32? Let's do the 32. What is in 32? Write a short sequence of instructions that divides the number in BL by the number in CL. This was in the quiz, right?
Yes.
Okay, and then multiply the result by 2. Final answer must be a 16-bit number stored in the DX register. So first we want to multiply the number in BL by the CL. So let's write down what we are going to do. BL by CL divide. Then multiplied by?
2.
Multiplied by 2. Now you know the rule of division. Numerator has to be the double, right? So we say here first, move BL to AL. The numerator has to be double and again in AX only. So once BL is in AL, now I say convert byte to make to protect the sign of the number. Okay? So this means now I have here BL in AX. Yes.
Can't we already say move BL to AX?
No. Remember the rule in chapter 4. The sizes have to be the same. This is what I found mistake also in the quizzes. Some of you are using instructions with different sizes of the registers. And we said in the beginning of chapter 4 that are movement instructions. Do not use the mixed sizes. Okay? So once I have it now, my value is in AX. Now I will say I'm dividing by CL. So this will be div CL, which means AX divided by CL. And the answer will be in
Yes.
this will be quotient and this will be remainder. Because this is division. Okay? Now what is the next? Multiply the result by 2. So what do I do? Move 2. Or you can directly use 2. Move to which register you want to use? DL, right? Now I have 2 and I want to multiply with the which value? No. Where is my answer of the division? In AX, right? But quotient is the value. This is remainder. Multiply with the quotient. You cannot multiply with the remainder. My quotient is here in AL. So I will say here mul DL, which means AL multiplied by DL. Let me leave a space and let me, I say here mul DL, which means AL multiplied by DL, which is 2, and answer again multiplication, isn't it? Okay? This is the multiplication. But again, this means I am overwriting the remainder, right? Are you getting the point now? See, after this multiplication, whatever is the answer, it is overwriting my, did I protect the remainder? So where shall I keep it? Move any register. AX is now occupied. Let's say DH and from AH. Okay? This is what I have.
So can we use CH?
You can use CH, yes. Even CL is also okay, but CL will be overwriting the original value, right? CH is also fine. So I divided it. I have quotient and remainder. Before multiplying 2 with the quotient, I am saving the remainder also. Of the first one. Now final, but not DH. Pick some other thing because here say answer should be in DSL. So which one shall I use? CH, right? So finally here I will say move from AX to DX. Now answer complete. So I'm moving this one, which is saving the remainder. Let's see if we can. This is not 3 and 4. This is, yeah, review of flex, right? Shall I leave this one? Shall I erase it now? Because nobody writes, you just take the photo. Suppose that the output of arithmetic instruction is stored in AX. So we have one operation done in AX, and it was addition of BX and CX. Assume BX is equal 5429 and CX is equal 897D. What is the final value in AX, and update the flex. Original flex are C5. Okay, so C5, let me write down. 5 is, and C is 1100. Okay, these are the flex. This one is a carry, parity, auxiliary, 0, sign. What are the other ones? Overflow, direction, trap. And the other one here is 9th one is the nth, which is not given. We will understand, since it could be 075, so we will understand as a 0. Considering that the flag here is 0 value, right? 0C5. Okay. So this is given now. Let's add. What do we get? 5429. Add 897D. Now add them. D is what?
13.
13 plus 9. 22. 22 minus 16 in hexadecimal, right? So 6 carry 1. 2 plus 1 is 3. 3 plus 7 is 10A. 9 plus 4 is 13, which is D. 8 plus 5 is 13, which is D. Okay. Do we have a carry?
No.
So this will be reset to 0. What is the parity? Parity means only check here in the lower byte. 1010 0110. Okay? 1 2 3 4, which is even. For even 1. So this will be changed to 1. What is it? Auxiliary. Auxiliary means, that means over here. Is there a carry from here to here?
Yes.
There is 1, right? So this is correct. Already 1, so we'll make it 1. What is next? 0 flag. Is the answer 0? No, right? So make it 0, right? Which is correct. Flag is just yes and no, right? Sign. What is this number? 1101. So sign has to be 1 here. Perfect. We do not know about this one. We do not know about this one. We do not know about this one. So we will keep these same, right? Now the only thing is overflows. Since we are adding it, there is no check on the overflow, right? Only we said overflow will be when we subtract and in the binary there is a borrow from most significant bit to least significant bit, right? Most of the, not least, but from most to next most significant bit. So this overflow remains 0 then. So what is now the value instead of C5? We have here 1 1 0 1, which is
15.
D, right? This is D, and this one is 0 1 1 0 6. This is the new flag we have. Okay. Let's do this one. You will have a full question like this. I told you before. These are only 4. You might see 12 to 13 instructions. Very big, right? So remember the instructions which we have covered in chapter 4 and 5. What is the first one? Move 45 to? So it will go to AL. AL is here, right? So since we have many, first let's check which instruction is to be done, right? 0 1 0, so it becomes 1000, which is this one. Okay? What is the first instruction? Since we are here, 45 to AL. What is 45 to AL? This 45 will go here, right? 45 went to AL. What is next? Move from AL to memory, right? AL is 45, and what is the memory? Do we have the DS? This is the DS. DS is 200 shift by 0. 2000 plus Bx is equal to 1000. 2000 plus 1000. 3000 plus 1, 2, 3, 4. Which means 4434, which means we are here. So in this one we will write the value of AL. 45. Okay, what is after that? Push Bx. You remember the rule for push? What is the rule for push? Decrement the address by 2, then write. Okay, do we know the address for stack? SS and SP will be given, right? So let's calculate the physical address. SS 0621 shift by 0, 6210 plus SP, which is 512. Add it. So what do you get? 06210 51, correct? 2276 06722. Since it is push, which means decrement by 2, so this means we will go to 20, right? 6720. Where is 6720? Over here. We went there, and we are pushing Bx, which is 1000. 00 is lower byte, 10 is higher byte. So this is 20 lower, 21 higher. So you keep that thing. Lower byte goes to the lower address, higher byte goes to the higher address. What is the last one? Do you remember? Load effective address to SI from the memory. Okay? So what is the memory now? Bx is 1000 and 0092, which is, so what do we do? We don't have to go to the memory because it says only load
And SR.
effective address. Try to understand again, remember the equation. So load only effective address. Address is only 1092. So 1092 will go to SR. This is SR 1092. Only the effective address. Okay? Now we finish this thing. Now let's go to the quiz and see if you have questions from here. Alia Al-Jabri.